My name is Wolfgang Kessling. I'm physicist and climate engineer at Transolar, Germany. We are here at the National University in Singapore at the School of Architecture. Transolar designed the climate concept for the School of Design 1 and 3 building. That have been existing buildings built in the 70s. They served architects as studio spaces, as maker spaces, seminar rooms. There have been lecture theaters, and professors and faculty members had their offices in this building. There was also the office of the Department of Architecture. An entire generation of Singaporean architects started their career here. About 40 plus years later, the buildings have not been in good shape, and it was time to review the existing. The operation of the building has been energy intense, and the spatial quality was quite low. These are typical conditions under which decisions are made for a low-budget refurbishment just to continue for a few years, or, if the budget allows, to demolish and replace the building. The School of Design, the Department of Architecture, wanted to go another path. They have been interested in the adaptive reuse of the existing structure. In this video, we briefly look on how the status was before refurbishment. We look onto how the design team explored the potential of the existing structure. Together with the design architect, we will have a walkthrough through the building, and we'll have a look on how is it operated today in full swing. The short film will end with touching base on the carbon story of the building. School of Design number 1 and 3 supposedly have been the first adaptive reuse buildings at NUS in Singapore for which a life cycle analysis was made. And it turned out that the embodied carbon as well as the operational carbon was quite low, roughly a factor 4 lower compared to conventional practice. This makes this project to an interesting and inspiring role model for adaptive reuse of existing structures in the tropics. This is how the building looked before. These are the west and the southwest facades. The opaque external louver screen blocks all direct sunlight. However, because the louvers extend so low, they also reduce diffuse daylight, blocking not only the natural light, but also the views to outside. Even just behind the facade, daylight levels were low. Artificial light was needed, and the view to the outside was poor. This is how the internal open studio looked like. At level 2, offices lined the facade, turning all other spaces into internal zones, requiring artificial light and mechanical ventilation around the clock. There was no view to outside, no access to the facade, no operable window, no natural ventilation, and no sense of orientation. At level 1, the situation was the same. No daylight, no view to outside, poor indoor air quality, low comfort, no spatial quality, very low floor-to-ceiling height, and dark, oppressive spaces. As one student summed it up, "I just want to be 1,000,000 miles away from here." But we also observed that the false ceiling contained large volumes, completely packed with mechanical systems. The historical sections, what we found, revealed large ceiling voids at all levels, typically 60 to 80 centimeters high, and in some places, such as level 1 and level 4, reaching up to 1.8 meters. That is substantial. In fact, the space was that tall that one could practically walk inside the false ceiling. We began to imagine what it would mean if all that hidden volume were reclaimed as part of the open spaces. With that thought, we envisioned brighter interiors with improved daylight, stronger connections between inside and outside, even the possibility of carving an atrium into the darker areas to enhance both natural light and ventilation. In a very simple way, we first visualized the space as it was, with the low false ceiling, and then compared it to the potential of the existing structure once the ceiling was removed. We also visualized the idea of carving an atrium into the building. The difference in light and spatial quality was remarkable. The potential of the existing structure became increasingly clear. The challenge, however, was how to deal with the massive mechanical systems and free up the ceiling voids. For this, it is essential to question why conventional mechanical systems are so large. The existing School of Design 3 building had been conceived as a sealed, fully air-conditioned box. In contrast, we explored the potential of tropical thermal zoning, combining natural ventilation with hybrid cooling, and putting air conditioning only to spaces where it was truly necessary. In the end, we adopted hybrid cooling for the main studio spaces. Hybrid cooling combines a supply of fresh air with elevated airspeed. The supply air ductwork is small and flat, with no return air ducts. The exhaust air simply spills over into the circulation areas. This diagram illustrates the shading concept. The pre-soleil system is offset against the floor levels. This provides solar gain control while improving the daylight redirection with a light shelf. This is the direct comparison before and after. The construction site images reveal how the false ceiling was packed with mechanical systems, and how much space was given to oversized air ducts occupying a significant portion of the building's height. This photo makes the dimensions of these spaces clear. This image illustrates also how deep the opaque louvers blocked all the views and the daylight. The last image shows the large floor openings that were cut into the slabs as part of the design. We will discuss that with the designer Eric Leheureux and talk about his architectural vision for the building's refurbishment.
It's great to see you.
Hi Eric,
Hi.
good to see you.
Nice to see you.
We are here at the School of Design 1 and 3 together with Eric. Eric was professor and vice dean at the Department of Architecture, and we actually worked together on the implementation of a high comfort, low energy concept for the School of Design number 4. And at that time, it became more and more the question, what to do with the existing buildings, what to do with the School of Design 1 and the School of Design 3 building in front of us, because they have been a little outdated, they have not been good in the questions we just try to resolve with School of Design number 4. And I'm happy, Eric, that you join me today, and we have a short walk through the building to understand how we implemented as a design team ideas of biophilic climate design and a great tropical architecture, and how Eric, as the designer and the architect of the refurbishment finally of the building, turned it into this beautiful building. Thank you, Eric, for joining, and we probably walk in and you tell us something about your ideas how to translate this space into something which has architectural importance for a school.
But maybe before we go in the front door, it's important to understand where we are. We're between SD1, which is to my left, and SD3 to the right. And this is a major axis on the campus where many of our students get off the bus and then enter into NUS proper. So it was important that the design had important dignity and also had a front door to the Department of Architecture which never existed, which is right here. And we're going to take you through that and then talk about some of the interesting innovations on the inside.
Let's do that. I think it's a very interesting already opening space where we are, where you decided to cut a knuckle into a building. What was your architectural idea behind this architectural gesture?
Maybe we should just situate ourselves. We've just come through the front door. We have an amazing exhibition space at the front so that students come in and see how architecture is displayed, how we can talk about architecture, how it can be presented on the wall. So that's an important kind of front position where we are right now. And if you recall, which I know you do, in SD3, each of the floors was kind of separated from one another. So you had no idea what was going on the second floor or the third floor. So our students were distributed throughout, and there was no space of kind of social cohesion, or there was no heart for the architecture building. And it was important that we opened that up and created this center, this social heart, where all of our students circulate, can look down into the other studios, so that second-year students are learning from first-year students, or first-year students are learning from fourth-year students. And it becomes a kind of almost engine of architectural education right in the center of the department.
Right, and I can see and I remember how that translated the space from separated boxes, layers, into a huge open space, and now also is a social space all around that stairs. But also it shows a kind of, I think, different way to work with space. Open spaces from boxes to connected spaces. And I think that's somehow related to what even transformed that space even more.
Where we are on the window wall, the ceilings and the mechanical plenum were at the kind of line of where that top mullion is. So you can imagine it's almost 1.5 meters below where the slab was. So it was a very tight, kind of minimal space, and it was kind of almost claustrophobic. So by opening it up and creating really this fantastic generosity for our students to work, to learn, to debate, right next to this social center was an important attribute of the design.
Where we just walked through here, and where we go up here, it was the darkest cave, what I remember. It was a dark cave where no daylight entered. The ceiling was so low, I could touch with my hands the ceiling here, and that was the space where an entire generation of architects learned about quality of space. And I saw a huge conflict in this.
Yeah, we were almost ironically on one of the soffits here, where most of the master's thesis students would be learning or doing their final degree project, which, just as you mentioned, very dark, stuffy, really one of the worst spaces in the building originally. Someone had put a graffiti on the soffit, said, "I just want to be 1,000,000 miles away from here." So I think that was almost a kind of ambit for us to take on and really change in a radical way on what the space could be and make it one of the best spaces in the building.
Absolutely.
So to open that up, to create linkages between the upper floor was really important, to have good lighting, and the The balustrade here is also transparent, that allows some views out to the jungle through the second floor, and to have the views directly over the design studio on this level out to the jungle. We get those views. We also can see into all the action that is happening in the studio below. So this becomes a great almost kind of perch onto the design education that's happening below, and it's a great place to study, to make models, to converse. So what was one of the worst spaces in the buildings become one of the best.
Now we are in the level 2 in the design studios. And that was the place I remember well. I think it was this line where all the professor booths have been. I think you had your studio.
Yeah, my office was just about there with maybe a view to the outside, but because of that, the students had no view.
Right.
And one of the important things that we were able to do was to open all that up by moving the professor offices to SD1. That allows for great views on both sides of the building. It also allows the building to be ventilated, cross-ventilated, when the windows can be opened on each side.
And I think what also happened here in this space is that we freed the false ceiling. We still have installations here, but we have a way lighter installation for the hybrid cooling, which brings in the fresh air. And what we also see is what was part of our joint work, how to design the elements of light, how to design the elements of ceiling fans, which are important for comfort, and actually how to integrate everything in a nice and beautiful way that it could be exposed like this. Here we see the duct, the supply air duct for the hybrid cooling, that it could be exposed like this, but creates a more free and more ample space.
If you remember, the ceiling originally was at that mullion line here, so quite low, and it was just the mechanical stuff up in the ceiling. By removing that, we open up the space, we get a little bit more volume, but of course by opening it up, we have to put a lot more care into the design of the system. So a lot of attention was to all the conduit runs. We also have an acoustic spray, which is on this side of the beam for the acoustic environment. And we have a white painted ceiling here to allow the daylight to bounce off the light shelf, which is at that mullion level.
I think you need to explain that better, because you also put a lot of attention how to design for excellent daylight conditions.
So light is coming in, we're facing west, it's bouncing, you can see the glow in the clear story. It's bouncing off that, bouncing off this white ceiling to drive daylight as deep into the floor plate as possible. So it really creates a great kind of atmosphere with natural daylight, views to the outside. And if we look more closely at the building envelope, for us, I think it was important that the building envelope isn't just the outside. It's not just the facade, but it's really this very deep space that comes all the way from the outside to the inside and has real performance capabilities. Driving daylight on the top, but also with the screen that is below the light shelf, cutting glare that comes from the afternoon sun. So it's making the quality of the daylight in the afternoon really great to be here. And it also, I think, in a way, amplifies the sunlight in the atmosphere.
It definitely improves the feeling where you are in the building. You know where you are. You see the green here, you see the outside here, you hear that noisy street. Still, you can open for ventilation if you like to. Easy to do this. And what is also, I close it because of noise. Also, because we implemented that hybrid cooling, which brings indoor temperature closer to outdoor temperature, it creates a more natural transition between outdoors and indoors. Eric, we are coming to the veranda on the 4th floor, which is actually the connecting line, the connecting space, the circulation area to bring all the students to the lecture theaters. Similar to what we have seen in the floors below, you remove the false ceiling, you put all the mechanical stuff in a nice way, it's all serving the spaces, and you also change the facade here to create that nice space. So I think what we learned here is that the ideas of transforming the facade as a part of the architectural language works for very different uses, actually.
Yeah, and creates a great outdoor thermal zone between, let's say, full daylight and rain, as we just saw, to a space that is kind of inside and outside. It's a great space for students to gather, to check their phone, to decompress after a busy lecture. But I think more than that, the building in its totality really serves as a role model. When we began this project in 2015, adaptive reuse and decarbonization were just in its infancy in this part of the world. And through a long 8-year period, but an important one, we've been able to make important changes both in bioclimatic design and integrating that, but also to make important spatial changes into the existing building to create two buildings really transformed for the 21st century. And I think if there's anything that those values that we've worked so hard to instill will change architectural education for the future.
Thank you very much. Thank you very much, Eric, to join us today, for give this insight into this inspiring building.
Retaining and adaptively reusing a structure carries deeper meaning. It raises the question of carbon emissions both in construction and in operation. To compare emissions between scenarios, we made a life cycle analysis for the project. To estimate embodied carbon emissions, the 3D model was used to calculate the masses of the main construction components, both those retained and those refurbished. At the time of the project, no tools or carbon inventories for construction materials were available in Singapore. We therefore relied on international databases to estimate a range of emissions for new constructions and refurbishment scenarios. The identified range is low compared to today reported carbon emissions for new constructions. Despite the uncertainties and limitations of the analysis, the adaptive refurbishment likely reduced embodied carbon emissions by 70 to 80%. How to reduce carbon emissions in operation? In the tropics, about 50 to 60% of the energy demand is related to air conditioning. Let's compare comfort and energy demand for cooling with a conventional air conditioning system and a hybrid cooling system. The image shows a psychromatic chart indicating the hourly climate data in gray dots and the cool and dry conditions in green achieved in the space with a conventional air conditioning system. Comfort is excellent. The system is designed to keep indoor conditions within what is labeled ASHRAE summer. The electrical energy demand for cooling is high. With hybrid cooling, this energy demand is reduced roughly by 50%. The conditions in the space are not within the ASHRAE summer comfort, which is only applicable without any air movement. The conditions are warmer and more humid, but perceived as comfortable because of elevated airspeed. In summary, hybrid cooling is an effective strategy to reduce energy demand for cooling and ventilation. Yet, in low energy buildings, not only cooling but all other electrical loads must also be carefully optimized. During the concept phase, we worked with a conservative estimate. In operation, the actual measured demand turned out to be lower, corresponding to lower carbon emissions in the range of about 25 kg CO2 emissions per square meter in year. We have learned that developing a carbon story is a valuable tool in the design process. It brings together the emissions from both construction and operation. As different stakeholders become involved throughout the process, a carbon story helps to keep everyone aligned with the agreed sustainability objectives. This diagram was created during the concept phase. The brown segment shows the embodied carbon, while the blue represents a conservative estimate for operational carbon emissions per square meter over 30 years. Adaptive reuse avoids about 80% of emissions compared to constructing a new building. However, emissions from conventional operations still dominate the total. With a hybrid cooling and optimized energy demand, future carbon emissions are directly avoided. The reductions enable a shift to renewable energy on site. The roof, and in this case a renewable microgrid, can provide the low carbon energy. This reduces operational carbon emissions to nearly zero. This diagram provides an alternative representation of carbon emissions over time. So if there are two key messages I take away from this project, then they are design matters and low carbon matters. This is not just any building here. It is where the next generation of architectural students are educated, and they can directly learn from this building. I think it was Winston Churchill who said, "First we shape our buildings, then they shape us." And this is exactly learning from the existing. It's not textbook learning. It's experiencing a tropical building with great daylight design, great indoor air quality, great thermal comfort, and getting inspired for the future practice as a young architect. We need to reduce carbon emissions. This project is an excellent example how a structure, once perceived as outdated, as uncomfortable and energy intense, became translated into a high comfort, low carbon building. Today it's hard to imagine how it looked and performed before. And yet there are many buildings with a similar potential. So I hope that the School of Design building becomes an inspiration for adaptive reuse of buildings across the tropics.